Ravi and Amit for making me get rid of the embarrassment of being a speaker instead of being in the organizing committee. So also I must apologize for my half-baked results because these are not complete because the project assistant left in midstream, so that's why. So anyway, this is a joint work with Arnab, who is a PhD student at Siddharth Singh was the project assistant, but he is no longer. It's located somewhere, in between Chennai and Pondicherry, in that region D04. Okay. This is Chennai and this is Pondicherry, so somewhere here. Okay, so that particular site holds a number of nuclear facilities. So the need for wind field simulation along with measurements is obvious. And the Indira Gandhi Center for Atomic Research proposed a round-robin exercise for atmospheric flow field modeling. So we took upon ourselves, the choice was left to us, but given their choice, they would ideally like a WRF with a Kalman filter. But we have no plans of running a WRF or whatever. So we decided that we'll take a Kalman filter and then of course look for a linear model, because as we know Kalman filter is a linear filter. So we scouted for a model but could not find one that incorporated both Coriolis as well as a non-zero background. That is, when you linearize around a particular velocity profile, that is called as the background wind. So it's the linearization. Yes. Okay, why should we include Coriolis? This is a typical scenario of a sea breeze. You have warm land and then cool ocean there, and there's a circulation which sets up, and because of Coriolis, the planes it gets reversed. So it's good. It's important to include Coriolis force. Okay, so here are the set of equations. So these are basically hydrostatic linearized Boussinesq approximation in the XZ plane. So, and the Coriolis force is given by the linear term minus F and plus F there. This, instead of the vertical velocity, we have this hydrostatic approximation. B star is like a temperature. And this is of course the two-dimensional continuity equation. And Q star is a heating source, which looks something like that. It's a sort of a model, and the source is given by Q naught, and variation with respect to X and Z is given in that particular. It's basically a fit to some observations. And the coastline is at X star equal to 0, with land to the right and sea to the left. And the lower boundary is assumed to be flat, and so you have a 0 boundary condition for the vertical velocity, and the top is unbounded, and the decay condition applies. Capital U is a linearization. So the nonlinear term is linearized around U. Okay. N is what is called at some blunt isoelectric. It's just a constant which, yeah. Okay, so you non-dimensionalize this using that, that's not important. But finally the non-dimensional equations look like this. So essentially it's a sort of semi-hyperbolic system with that kind of things. So the most important thing to notice is that you can find these velocity u. U is nothing but u has gone into, here is u. So u is sitting here. So the v is that. And it has been shown by Grenier, Brenier and Renardi that this is an ill-post system. You can find a u which is ill-post. And ditto with boundary conditions. Oliger and Sundstrom in 78 showed that you can have some open boundary conditions on the top which will make it ill-post. And that it is ill-post with those boundary conditions in the hydrostatic is well known from many of these experiments. For instance, in this GCM numerical simulations, if you refine your mesh, you will get a totally new result. And but nevertheless, people do data assimilation. So one of the conjectures or one of the thesis we are trying to work on, can we have some observability and controllability results for this ill-post system? Okay. What Brenier has shown is that if you, for the nonlinear 2D Euler system, if your velocity profile, the horizontal velocity is convex, it is well post. But the convexity is not a long-term phenomenon. It breaks down in finite time. And how did he come up with that assumption? It's based on Rayleigh's stability criterion. From that, he somehow inferred that the Rayleigh stability criterion was based on convexity of the horizontal profiles, and very cleverly used that to show well-postedness for this. So, but definitely that system is ill-post, and this appeared in ARMA, Archive for Rational Mechanics. And what Arnab is trying to do is to get some observability estimates for this system, which is ill-post. Okay, so one can reduce this to a single equation, which looks like this in stream function formulation. And yeah, I must mention that in all the previous linear models, V was 0 and capital F was 0. So this, the new thing about this linear model is the incorporation of those two terms, for reasons I mentioned earlier. Okay, so this is the equation we have. X is from minus infinity to plus infinity, and then Z is from 0 to infinity. And take Fourier transform with respect to X, you get into a system like this. And again, using separation of variables, we look for solutions of psi tilde, which is a 2-point boundary value problem in Z. So you have a coefficient multiplying d square psi by Z. We didn't write that down, but you get a 2-point boundary value problem from Z equal to 0 to infinity for psi hat, and you use Sommerfeld radiation condition to kill exponentially growing solutions at infinity, and psi tilde, you can get that. And then finally you have this expression for the stream function. It looks horribly complicated after taking the inverse Fourier transform. And going back to the u, v variables, so this is u, and of course one can't decipher anything out of this, but the hope is that we plan to find some v which will make this ill-post. That is a future thing. So u looks like this, and w also looks in a similar fashion like this. Of course, only thing is best is to plot these solutions. So that's what Arnav has done, and here is the horizontal velocity as a function of the background wind. Okay, so this is for 0 and that is for 2, and what it seems to say is that the profiles lose sharp gradients near the coast, at the coast. And similar thing on the effect of latitude. That is, this tells us the dependence on the Coriolis force, because if you go back and look at this where is F? Yeah, it's well, I don't see that. So F, the variation of F is in terms of theta. Yeah, omega is there, F by omega. F is some omega times sine of the latitude. So F is just a function of latitude. And so if you see the variation with respect to latitude, it's a very similar thing. Namely, this is at 15 and that is at 25. So basically that term is getting multiplied by sine 15 and sine 25. And again, it seems to get, the sharp gradients seem to decrease. Of course, nothing significant to conclude out of this. And same thing with vertical velocity also. So this is the effect of background wind, and a similar result for the effect of latitude. So all you can say is just that gradients are just so we have those solutions. Now what we want to do is try to fit it to the data which has been measured at Kalpakkam. And of course, it has not yet been possible because, so here's the site where the measurements are made. So there are some, there is a 30-meter tower here, and there is one at the main gate of IG car, and another one at Anupuram. So most of these, the project tester has analyzed the data at Anupuram, and I just show some variations of that. One of the main problems, as also Emma mentioned, that the observed and model data are not the same. So we have to convert it into, but although from sonic anemometer, this is, you can get all the three velocities. So here's a typical plot which you have at 50 meters. So what is the description of this? Yeah. So it gives a plot at 50 meters on that date, and it is taken every 10 minutes, and it is averaged over that period, and so there's not much variation. And now if you look at this data at 8 meters, there's some variation, and so according to that analysis, it seems that maximum variations seem to take place at 8 meters height and at 2 meters. For rest of that thing, it seems to be almost a constant. So here you see, for instance, at 50 meters on, it's just a constant. And piecewise constants in some case on some particular date. And okay, 8 meters you see some variations. And yeah, so according to this analysis, the above trend continues for all this period, except and it breaks at about during October. So here you see another typical data like this. Yeah. Yeah. So some description of this variation. So here's another. Yeah. So the idea is that the final architecture of the project will be, there will be that model running and that station data tower and Kalman filter. I didn't write down those Kalman filter equations. I think it has been repeated ad nauseum, those Kalman equations. So that's the sort of thing we have developed. Actually, that code is ready, that Kalman filter code, and and final output is supposed to come out like this. The question is, how do we, what kind of system we need to use with just, or what kind of domain we should take. If we are going to solve in a bounded domain, for instance, this system, if we are going to solve in a bounded domain, in fact, there are theorems of observability for linear hyperbolic systems, which say that the boundary data should be, the observables should be at the boundary. Okay. So in other words, then some observability theorem holds for linear hyperbolic systems. Of course, in this case we have, so our first task is to find out what kind of domain we should take in this region. And of course, in the idealized example, the coastline was just a straight line. Here the coast, as you know, it's like this. So we just have some 3 points here. Now the question is, based on the theory on observability, should we have our domain suited so that the boundary is at these points where the observations are made, or we should just go ahead and take those expressions, complicated analytical expressions are there, just use that as a functional fit, and then use the time series of data. But again, it's only at a couple of points. And there, you see, the observations are only at some 4 or 5 points in height. So how to go about this? The strategy is all, as I said, still not yet fully resolved. So it's an ongoing project, and so I just told you what the status is at the moment. So that's it. Yeah, there exists a U background wind for which it is ill post. Yes, 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 yes.
Put that into the end.
Yeah, it is like a short-term instability. Namely, you take exponential of imaginary part, and that constant multiplying that is actually again imagined. Show that it has imaginary roots, so that the solutions are exponentially growing.
So if you put that into your expressions,
Yes.
the solutions simply go
Yeah.
to
Yes. For nonlinear system, there's finite time blow up for these equations. Yeah.
but for the linear equations,
For linear equations, yes. There is an explicit U which is done by Renardi.
for which there is a finite time blow.
No, not finite time blow. Ill post. Exponential growth between two trajectories.
There are no further questions, then call next speaker.